Hi, I wanted to clarify a few things based on questions I've gotten in my office hours and questions I think that might come up while you're doing the pledge problem. So it all comes down, I've got 3 points, okay? So point number 1 is that all floors are being treated exactly the same. Oh, sorry. Wrong time. Here we go. Point 1 is about the pledge problem. So in the pledge problem, you have a case where you have a tuning fork over an open tube or open closed tube or something, some kind of tube. So there's one demonstration and a little effect I never showed you in class. It's probably talked about in the book, but I want to make sure you understand what's going on. So if you put a tuning fork like this, which lets out just a little bit of sound, right? It shakes, these vibrate, it lets out sound, but it's so soft you probably can't even hear it. I'll get closer in a minute and you might be able to hear it. So very weak sound. But if we put it near, while it's ringing, a resonant cavity like this, this is open closed tube, and you put it in front of this tube, it gets all the air molecules in the tube going in a standing wave like we talked about, and it makes it louder. Okay? So let me see if I can show you real quick. I'm going to get real close. Don't get afraid. Here we go. So you probably hear the high pitch from this fork. This is supposed to happen for the low pitch. But I'll stop talking now because I'm going to mess with the audio so that you can hear this. So you should have heard the sound get louder when it's near the little cavity there. So all that's happening is that one is exciting the other. And all you really need to know is that if a problem talks about a tuning fork is near a tube and you hear a loud sound at some point, that just means that the tuning fork's frequency matches a standing wave in the cavity. It doesn't have to be the fundamental. It could be a higher, m equals 1, m equals 2, whatever you want it to be. But the two match. And the frequency occurring is always the frequency of the tuning fork. Okay? So I never told you that. I never showed you that. We ended up using it on the pledge, so I just wanted to point it out. That was point 1. See, point 2 is about the difference between interference and standing waves. We sort of talked about both similar variables, so let's make it clear. And the reason this comes up is because of the problem where you have two speakers facing each other. Remember this? And you're thinking about the interference between the two waves that are approaching each other. Right? So we said, oh, well, if we want it to be constructive, where is it constructive? It's constructive where the difference in phase equals the difference in distance over lambda times 2 pi plus the difference in phase constant. And it's constructive if those are equal to 0, 2 pi, or 4 pi, etc. I know you hate this formula, but you just got to get used to it. Okay? So what we know is that there must therefore be constructive interference right between them, because that has the case that they have the same, we called it 1 and 2, they have the same distance. Right? So x1 equals x2. So x1 minus x2 is 0. This term is 0. If we assume they start in phase, that term is 0. This term is 0. So it must be constructive. So it must be that when this one sends a high peak here, this one has a high peak there, so you have a high part of the phase here of the wave. They are constructive. But it's also true when they're down. If they're both down, you get a low part like this. So we plot the whole thing, you'd see something kind of like this. And then a half cycle later, you'd see something kind of like this. And you say, that doesn't look like interference, that looks like a standing wave. And in fact, this case will make a pattern that looks a lot like a standing wave. In fact, you could even call that an antinode, unless you define antinode as a property of the standing wave. In this case, if an anode is just where you have a high variation, that's an antinode. You could define this as a node. Those are actually nodes there. Okay? And then another antinode, another node. So what keeps this from being a standing wave? What keeps it from being a standing wave is that there's nothing special happening at the edge. Okay? So in this case, this is not clamped or open. You don't have to have a certain pressure here. So the pressure wave being made by this speaker gives some value here, and the little diaphragm making a pressure wave by this speaker gives some value here, and they can add, and you don't have to have a node or any node at the ends. So the physical effect looks a lot like a standing wave, but if you define a standing wave as having these definite boundary conditions, then it's not a standing wave. And that actually makes a big difference because remember, it's the boundary conditions that make a standing wave only happen at certain frequencies. Okay, so if we go back to our now interference, our standing wave idea, that was, for example, a tube. Now let's make it open. All right, so we know it has to be for pressure, it has to be P equals 0 here and P equals 0 here. 0 from atmosphere, we say atmosphere 0. So you're going to get something, and it only fits for certain wavelengths and certain frequencies. That's because of the edges being clamped. Here the edges aren't clamped. So you actually get nodes and antinodes for any frequency that you apply with these two speakers when they're facing each other. Okay, so nodes and antinodes aren't that special. It's the discrete specific frequencies that are special. That's what makes standing waves special. Let's see, so that's what I wanted to say about that. This will occur at all frequencies, discrete frequencies. And then you may say, no, well, why? Wait, what happened to constructive and destructive interference? Remember our film said it's 0 everywhere, or it's constructive everywhere. And that's another difference that we didn't get into, that I now realize we should have, because it probably created confusion. But back to interference, it depends on if the waves are going the same direction or opposite directions. So let's think about the interference we talked about. These two waves, both going forward, will give you constructive interference. Right? They're moving together. These two always add to a higher value. These two always add to a lower value. Constructive interference. These two waves, if they're both moving forward, will give you destructive interference. Right? High, low, low, high. It'll always add to 0 if you were to add those two waves up. But if they're going the opposite directions, then it's not going to always be constructive or destructive. It's going to go past each other, and lots of exciting stuff happens, and this will actually happen. You'll get the antinodes and nodes if they're the same frequency and wavelength. Right? So we didn't really talk about waves going past each other, except in sort of this one homework. And then if you read the book from the chapter from cover to cover, you'll see you actually can think about a standing wave as an interference problem where the waves are going opposite directions. If you think of it as a wave going this way and then bouncing off one end and coming back, then you've got propagating waves going past each other, creates nodes and antinodes, just like we said it does here. But because the edges matter, it has discrete frequencies. And this actually makes one sort of, this makes a little effect that I won't get into the math here. But it does mean one interesting thing, and that is here, if we were to move, we talked about how you move some distance d, it actually has twice the effect on the interference, because you got d farther from this one and d closer to that one. There was sort of a factor of 2 in there compared to just moving one of these d. Well, a standing wave also has that factor of 2. If you change the length of the tube by, delta L, the effect on interference is that you change it by 2 delta L, right? Because the wave has to go forward and the wave has to come back for the new delta L. So if you look carefully at the conditions of lengths to get a standing wave and delta x's to get constructive interference, you'll see there's a factor of 2 difference. And that's the reason. In interference, you're usually just moving one wave. Here, if you lengthen the tube, you move 2 waves. So if you ever notice that factor of 2 and it bothers you, that's what's going on. Okay, so that's point 2, the difference and similarities of interference and standing waves. Point 3 is the much dreaded thin film interference. And the way I was drawing all those diagrams is 100% correct, but I do want to show you, I think I now understand why there was so much confusion about those diagrams. And here I'm talking about when the light hits the glass and bounces back and all that. You remember. Okay, so first let's think, how did we introduce it? We talked about how when a string reflects off the pole is like a higher index interface, like a heavier medium. So we said, the string bounces back and has a negative pulse. And that's what we call a pi phase shift. Right, a half wave, pi, 180 degree, whatever you want to call it, phase shift. Clearly that's what it is. So we said, let's use that idea for light. And let's think about our anti-reflection coatings, our thin films on a glass substrate. So here we have air here, n equals 1. We have some film here, n equals 1.3. We have glass here, n equals 1.5. We're not going to do the whole thing, just the confusing part. And I said, okay, let's imagine we have an incident wave like this. Hits the front glass. So we'll call this an incident. It's going that way. Right? We'll draw the little line, the little axis like that. We said, first, let's think about the reflection off the front. Reflection off the front is hitting a higher index, like this did, so it has a pi phase shift. So I said, okay, well, if this was going to go up, if it has a pi phase shift, it now goes down. So let's draw the reflected wave going down like that. Okay. And you look at that, and you say, where's the pi phase shift? There's no pi phase shift here, because it's in phase with the incident. That looks weird. But before we explain it, let's just draw it again. Let me pick a different phase to draw it at. Why don't we say it's like this incident. And let's say the reflected wave, this is supposed to be up and going down, but pi phase shift, down going up. All right, and that's the reflected. And then you say, okay, well, that makes sense. That's a pi phase shift. But we did the exact same thing. We just drew it in a slightly different point in phase. So what's the deal? So here's the deal. You can't just look at this drawing and immediately see if it's a pi phase shift just by overlapping these sinusoids. It's a little more complicated than that. So it doesn't just look like this, because this pulse, mathematically, if you had to describe it, it's a sum of an infinite number of sinusoids with different frequencies, different amplitudes, and different phases. You could plot all those sinusoids together, add them up by superposition, and it would make this shape. And as this shape bounces, it evolves and does this. And the reason it does that is because every little sinusoid also has a pi phase shift. Okay? But when a sinusoid has a pi phase shift, it's not this obvious. But let me prove to you that this has a pi phase shift. Look at this. Where's the front? Let's imagine this isn't a continuous sinusoid. It's just a sinusoidal pulse. Where's the front? This is the front. Where's the back? There's the back. It's going that way. Now it's coming this way. Where's the front? There's the front. Where's the back? There's the back. Clearly, it is a pi phase shift. The front was down, the back was up. Now, the front's up and the back's down. Just like this. It's all confusing because of the point in phase that I chose to draw. What about this one? Here's the front, and here's the back. What about here? Here's the front, and here's the back. Both are up, and now both are down. Okay? So it's not as simple as just looking at this and looking at this. Visual is good, but sometimes visual screws you. Let's see, so that was one confusion about that. And then the other was, if it looks like this, how are we calling that destructive? We're designing an anti-reflection coating here. I said it's destructive. Why do these two look the same? And there, you're just making the simple mistake is that we're not interfering the incident and the front reflected wave. We're interfering the reflected wave and the back reflected wave. Right? So this one and the one that came off back here. And by the time this one got out, these were always out of phase. So don't make the minor mistake of worrying about these two. That's why often, like in the homework problem, when you're designing, oh no, that's on the play problem. So on the play problem, there's something like this where we say it's a small angle. And the reason we say it's at a small angle is we don't want you to think you have to worry about interfering the incident and reflected wave. You're interfering the two from the film. I don't think I'm giving too much away. That's what we've been talking about for over a week. If we were trying to interfere this and this, or superpose these two, we would be doing this. We don't want to do this. So here we want to just focus on interference. Okay, so there's 3 points that may help as you keep